Let's take a look at a brand new type of integral. Well, not really a brand new type of integral, just a new way of kind of looking at it. Up until now, when we were doing a regular integral, and we did like the integral from a to b, who knows, some f of x dx, we were adding up all these values along the line along the x-axis from a to b. So we were integrating across a line from here to here, and we were adding up all the values that the curve had. But what if we didn't want to move in just an x direction or y direction? Well, a new type of integral is called a line integral. And what we're going to actually do is we're going to add up all the values of some function as we move along a curve. Now, since we're moving along a curve, the direction we're going to move in is actually along the curve itself. So one kind of idea here that you'll generally see in most textbooks, if we were going to integrate this from this little segment, we would have this defined as some vector valued curve, and that parameter would run from, I don't know, I'm just going to say like 0 to 1. That would generate the piece of the curve from A to B. So to do that, what we would do is we would integrate across this curve. Now, if you think about that, if we're adding up all the values on that curve, if this function had to deal with something like density, if we added up all the density as we moved along this curve, you can think about that as kind of finding the mass of that area of the wire. So let's take a look at an example how we actually do a line integral. Let's say we wanted to find the integral around the curve C of some x ds, where the curve is defined to be, let's do the one we already did parameterization on from last time. Let's say that this is our curve. Okay, so along this curve, we've already decided if we call this one C1 and C2. I'm going to run through this kind of quick because we did it in the last lecture. We said for the first curve, we could parameterize this as t squared as long as t runs from 0 to 1. And C2, that part of the curve was 1 minus t, 1 minus t. And again, we're going to run that from 0 to 1. So to do this line integral, we're actually going to break it into two pieces. We're going to do the line integral for C1 and then the line integral for C2. And then we know that the curve is equal to the two pieces together. Okay, so the last thing we need is ds. Now we've already seen ds a while ago. We saw that ds, a little piece of the curve, was the square root of x prime of t squared, y prime of t squared, if it was in parametric form, or with our vector values functions, we saw this as the magnitude of r prime of t. So when we set this up, we're going to have two integrals to set up. We're going to do the integral for C1 and the integral for C2. So let's see, for C1, let me start back over here so we got a little bit more room. I have to erase all this. So when we're on C1, we're going to do the integral. When we're on C1, x is t, right? It's because we've got to turn everything into our parameters. So x is t, and ds. Well, on C1, what would ds be equal to? ds would be equal to the square root of the x prime squared. So x prime squared is just going to be 1 squared plus the y part squared, well, derivative, so 2t squared dt. So this ends up becoming the integral of t, that was the x that was inside the argument, and ds is 1 plus 4t squared dt. Now where do the bounds go from here? Well, since we're integrating with respect to our parameter, on C1 our parameter goes from 0 to 1. All right, well this is just a regular u substitution. Let's run through this. U is 1 plus 4t squared, du is 8t dt. Notice here we don't have an 8t, so we can put a 1/8 out front and put the 8t in here. 1 plus 4t squared dt. We're going from 0 to 1. Now this is just the integral, and I'm going to leave off my bounds for a second, the square root of u du. There's our du piece. So that's u to the 1/2, so add 1 to the power, we get 3/2, multiplied by the reciprocal, we get 2/3. Now remember, we got to put back what u was, so this is going to be for 1/12, 1 plus 4t squared to the 3/2, and we still need to evaluate that from 0 to 1. Now I got to get some of this out of here, so we're going to have to remind ourselves what that was here in just a little bit. We'll write it back up there. Okay, so top endpoint minus the bottom endpoint. So when we plug in the top endpoint, we're going to get 5. So this is 1/12, 5 to the 3/2. Minus, when we plug in the bottom endpoint, that's just going to be 1 to the 3/2. So that's just 1. So this is going to be 1/12. Okay, so without a calculator, that's about the best that we're going to do. So that's for the first part. So now let's take a look what happens when we're on C2. Now remember, on C2, we need to write this up here again, R of t was defined to be 1 minus t, 1 minus t, and we ran that from 0 to 1. We also need to know what ds is on here. Well, ds is the derivative of the x component squared plus the derivative of the y component squared dt. So this one's easy. ds is just the square root of 2 dt. So when we go to set this up, just a quick reminder, remember we're trying to do the integral around c of x ds. When we're on C2, x is equal to 1 minus t, ds is equal to the square root of 2 dt. Now, as we move along the curve, we know our parameter dt goes from 0 to 1. All right, the square root of 2 is just a constant. We need to integrate 1 minus t dt. Square root of 2, that's t minus 1/2 t squared from 0 to 1. Top endpoint minus the bottom endpoint. We put in the top endpoint, that's 1 minus 1/2. That's 1/2 minus, and we put in 0, so this is just the square root of 2 over 2. All right, so let's put all of our information together now. So we know this, we're integrating c of x ds, which, since we broke this up into 2 pieces, it's going to be the integral of c1 x ds plus the integral for c2 x ds. So our answer here, the integral on c x ds, is going to be our first piece, 1/12, 5 to the 3/2 minus 1/12 plus square root of 2 over 2. All right, so when we're doing a line integral, if you're going to break it into each pieces, you do each integral for each portion of the curve that you have broken it into.